Hello students, welcome to lecture 8 of our online chemistry classes. In the last class we completed voids, type of voids, their coordination number, and to calculate the formula of unit cell using information, how many voids are occupied, which type of voids are occupied, all this part we have completed. Now today we will go ahead and we learn about the packing efficiency. Packing efficiency. Packing efficiency of cubic crystal system. Now why we are learning packing efficiency? Because in whatever way you arrange the spheres, there is always some unoccupied space because they are spherical. So when spheres are arranged, there is bound to be a vacant space, empty space. We call it as voids. So we want to know what is the packing efficiency of the cubic crystal system. We have three crystal system in cubic. Possible variations are three. One is simple or primitive cubic unit cell, another is body centered cubic unit cell, and third is face centered cubic unit cell. We learn many points regarding those type of crystal systems. But first we must know what is meant by packing efficiency. So packing efficiency is nothing but percentage of total space filled by particles. And by particles we mean it can be atoms, it can be ions, or it can be molecules. Already we discussed about this word. So it is the percentage of total space occupied. Filled means occupied by the particle. It's called as packing efficiency. We have another word called as packing fraction. Fraction is ratio. That it means the fraction of total space filled by particles. What is fraction? Another is percentage. Percentage is nothing but fraction multiplied by 100. So packing efficiency calculation is very important part, and it can be asked for 3 marks in the annual examination, and many MCQs can be framed on this part. So I have to listen very carefully as always. So packing efficiency, we can write formula: volume occupied by particles divided by volume of units. If we write only this, it would be packing fraction. But if we multiply it by 100, it becomes packing efficiency. Volume occupied by particles divided by volume of unit cell multiplied by 100 is the packing efficiency. Now this first part, volume occupied by particles, we can split this in two components. We can say number of particles per unit cell multiplied by volume of particle divided by volume of unit cell multiplied by 100. This is the formula which we will use. Packing efficiency is equal to number of particles per unit cell multiplied by volume of particle divided by volume of unit cell. Now number of particles per unit cell we know that it is simple, or we call it as primitive cubic unit cell. Cubic unit cell. The number of particles per unit cell is 1 because they are occupied only at corner. 8 corners multiplied by 1 by 8 contribution is equal to 1. If it is body centered cubic unit cell, it is 2. And if it is face centered cubic unit cell, that equals to 4. So this part, number of particles per unit cell, already known to us. What is the volume of particle? Particle we are assuming it as sphere. So we can say volume of sphere is equal to 4 by 3 pi r cube. Because particles we assume it as spherical, and the volume of sphere is 4 by 3 pi r cube. What is the volume of unit cell? We are considering it as a cubic system. So unit cell is nothing but A into A into A. A is the edge length. So it is A cube. It is nothing but edge length and cube of that. So these are the 3 components of packing efficiency, of course multiplied by 100. Number of particles per unit cell, they can be 1 for simple cubic unit cell, 2 for BCC, 4 can be FCC. Volume of particle 4 by 3 pi r cube, and volume of unit cell is A cube, its length cube, multiplied by 100. Now we will do this calculations in first simple cubic unit cell, then in body centered cubic unit cell, and then face centered cubic unit cell. And we will have very important relations of all these edge length and distance between nearest neighbors and radius and packing efficiency, and all these results we need to understand and we need to recall them when they are needed, right? So first we calculate packing efficiency of simple cubic unit cell. So I have to write some derivation in 2-3 steps, but these are very simple derivation. If you practice them 1-2 times, you will easily understand. So first I am writing packing efficiency of simple, or another name for simple is primitive, where particles are present only on corners, and that is cubic unit cell. So this carries 3 marks, already I have told you. We have to start with the diagram. We have to draw only 2 spheres here. 2 spheres, like this, 2 spheres, side by side. And after drawing these 2 spheres, we have to take their centers, because these are lattice points, and we have to make one plane here like this, one more plane at this somewhat slanted location. We have to create like this, and then this cube is created over here like this. We can name them as A, B, C, D, E, F, G, H. These particles. This is radius R, this is radius R, and this distance is the edge length. And this is simple cubic unit cell. Then we can start the derivation. We can say radius of particle is equal to small r. That's why volume of particle is equal to 4 by 3 pi r cube. Edge length of unit cell is equal to A. Volume of unit cell is equal to A cube. Number of particles per unit cell equals to 1, because this is simple cubic unit cell. A is equal to 2 times of radius, because this is radius, so this distance is nothing but 2 times of radius. That's why A cube is equal to 2 times of radius, cube of that, it is 8r cube. So A cube is equal to 8r cube. Then we have to write the formula of packing efficiency. Packing efficiency is equal to number of particles per unit cell multiplied by volume of particle divided by volume of unit cell. Number of particles per unit cell, as is simple cubic unit cell 1, and of course multiplied by 100. Volume of particle is 4 by 3 pi r cube, because particles are spherical. Volume of unit cell is A cube, and A cube is 8r cube, and this multiplied by 100. So it is 1 by 1, 4 by 3 pi r cube divided by 8r cube multiplied by 100. R cube you can cancel. 4 2s are 8. So it is pi by 6 multiplied by 100. Pi is 3.142 divided by 6 into 100, and that equals to 52.4%. That is the packing efficiency. So packing efficiency is 52.4%. And what is the percentage of empty space or void here? It is 100 minus 52.4. It is 6, so it is 13, and that's why it is 100 minus 52.4. It is 6137, and that's why it is 6, so it is 4. So it is 47.6% is the empty space. So this is all about the packing efficiency of simple cubic units. Very simple. Draw diagram very neatly. 2 times of radius is equal to 8j. Write this radius of particles are, volume of particles 4 by 3 pi r cube. Its length is A. Volume of unit cell is A cube. And number of particles per unit cell is 1. A equals to 2 times of radius. A cube is equal to 2 times of radius cube. A cube is equal to 8r cube. Packing efficiency is number of particles per unit cell 1. Volume of particle 4 by 3 pi r cube. Volume of unit cell is 8r cube into 100. That becomes pi by 6 into 100. It becomes 52.4%. So it carries 3 marks. Diagram carries mark. This packing efficiency formula also carries mark, and of course these steps also carries mark. So not at all difficult derivation. You practice it and you will understand how we have to write it. So this is for simple cubic unit cell. We have to again calculate the packing efficiency of, we can say, face centered cubic unit cell. 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 This is called as FCC, like this. Now I have to draw the diagram. And when we draw a diagram, see what type of diagram we have to draw. We draw spheres like this one. Like this. And again, and then create cube here. This type of diagram. On the face, these three atoms are there, and then you have to draw this type of face diagram, and you have to do A, B, C, D, E, F, G, H. This is edge length A, AB is A, BC is also A, and this face diagonal we call it as B, and its value is from this part to this part is radius. This is radius. This also radius and this also radius. So this face diagonal is equal to R plus R plus R plus R equals to 4 times of radius. That will mention. The first point is, then we have to give the reading here, FCC, face centered cubic unit cell. Even though it will not appear as a perfect cube, but you have to draw a diagram like this because diagram here is marked. Radius of particle is equal to R, that will remain as it is, that is not changed here. Volume of particle is 4 by 3 pi r cube, that is also a constant formula. Edge length of unit cell is A, volume of unit cell is A cube, number of particles per unit cell in FCC, 8 corners into 1 by 8 contribution plus 6 face center multiplied by 1 by 2 contribution, and that happens to be 4. This already we know. Now our derivation will be of different type. Packing efficiency formula is also same, so I will not drop that. I will use that at some point of this derivation. We need to add one more point here. Face diagonal is equal to B. This one more parameter we are introducing. Then we are trying to triangle ABC. This triangle I am considering A, B, C, and this part, right? In triangle ABC, we can use the Pythagoras theorem and we can write AC square. AC square is equal to AB square plus BC square. Yes, Pythagoras theorem we are using here. AC square is B square. AB square is A square. BC square is A square. So B square is equal to 2A square. And that's why B is equal to square root of 2E. So this we have calculated the value of B. now we can mention here as the phase diagonal is equal to B equals to 4 times of radius, isn't it? Because B is equal to radius, 4 times of radius. So we can write this B value as root 2A equals to 4 times of radius. That's why A equals to 4 times of radius divided by square root of 2. Now we can still simplify it because 4 can be written as 2 multiplied by square root of 2 into square root of 2, which is nothing but 2. 2 multiplied by 2 is 4. Radius divided by square root of 2. This square root of 2, this square root of 2 we can cancel. We can write A is equal to 2 times of square root of 2r. This is the value of A. So what is the A cube then? A cube is equal to 2 times of root 2r cube. 2 cube is 8 and root 2 cube is 2 root 2. So it is 8 into 2 is 16. Square root of 2 and r cube. Now we can put this in this formula. Number of particles per unit cell is 4 here. Volume of particle is 4 by 3 pi r cube. Volume of unit cell is 16 multiplied by square root of 2 multiplied by r cube multiplied by 100. Then I can simplify this as 4 by 3 pi r cube 16 to root 2 r cube into 100. 4 16, this 16 cancel. R cube also cancel. So what I am getting here is packing efficiency is equal to this pi multiplied by divided by 3 root 2 multiplied by 100. Pi value is 3.142. 3 into root 2 is 1.414 into 100. And this we have to remember that this is equals to 72%. 72.03 will come, and that equals to, we can just round it off to 72%. So that equals is equal to 74. Anyway, you can calculate this. That equals to 74%. You can round it off 74. So once again, half description is same. In this, we need not to change anything. Only number of particles per minute cell, depending on unit cell, we have to change that. So I have to calculate the value of body diameter. From that we get the radius, and we need to get the relation between edge length and radius, and then substitute that into the formula. Volume of unit cell is nothing but A cube. So we have substituted this here. Number of particles per unit cell is 4 because of FCC. Volume of particles 4 by 3 pi r cube multiplied by 100. So this is all about the FCC. Question can be asked for 3 mark. Diagram, description, formula of packing efficiency carries marks. So again you have to prepare this well, not at all difficult type of derivation it is. Now one last is there, which is nothing but packing efficiency of body center units, which we call it as BCC. BCC is nothing but body center cubic units. Diagram we need to change now. See the type of diagram I will draw here. For phase diagram, we have drawn that spheres in this slanting position outside. For BCC, we have to draw those spheres inside the units like this. And then we have to connect them and we have to create a cube here. Not at all difficult diagram. If you feel it is difficult, practice it. There is no other way. But diagram is very much compulsory. Question comes and if you do not draw diagram, your marks will be deducted. So now it is in body center. It is A, B, C, D, E, F, G, H. And then if I connect this I write C, which is body diagram. This FD is the phase diagram B, and this AD is edge length A. EF is also edge length A. ED is also edge length A. So this is edge length, this is edge length, this is edge length. This is body diagram and this is phase diagram, and this is BCC. Now I have to calculate this all packing efficiency part. For that, the first 5 points will be same. The radius of particle is small r. Volume of particle is 4 by 3 pi r cube. Edge length of unit cell is A. Volume of unit cell is A cube. Number of particles per unit cell is 2 here in BCC. 8 corners into 1 by 8 contribution plus 1 body center into 1 contribution. 1 plus 1 equals to 2. Then we have to write body diagonal is equal to C. And phase diagonal is equal to B. Now first we calculate the value of phase diagonal and then we calculate the value of body diagonal, because for phase diagonal we have 3 sides, EF, ED, FD. We need to know the value of FD. EF value and ED value is already known. So we have to say that in triangle E of D, this triangle, E of D, F D square, again Pythagoras theorem, because these are all right angles, is equal to E of square plus ED square. F D square is B square, E F square is A square and A square. So B square is equal to 2A square. It's the value of B square we are getting using the Pythagoras theorem. Now we'll use another one triangle. In triangle AFD, AF square, again we are using Pythagoras theorem, AF square is equal to FD square plus AD square. AF square is C square, AF square is C square, FD square is B square plus AD square is A square, and B square is equal to 2A square, already we know it, and this is A square, which happens to be 3A square. That's why C is equal to square root of 3A. This is the value of C we are getting, which is nothing but body diagonal. body diagonal is equal to root 3a and face diagonal is equal to root 2a. We have calculated that in last derivation. Now we have to again make slight modifications here because a cube value will be different and we have to make some changes in substitution and we get this equation. So you can write body diagonal is equal to C equals to root 3a, but that also happens to be 4 times of radius. How it becomes 4 times of radius? From this part to this part is radius. From this part to this part is radius. From this part to this part is radius. From this part to this part is also radius. So radius plus radius plus radius plus radius. 4 times of radius. So what is the value of A then? A equals to 4 times of radius divided by square root of 3. So what is A cube then? 4 times of radius divided by cube root of 3 and cube of that. 64 radius cube divided by root 3 into root 3 into root 3 cube is equal to 3 root 3. So we can substitute here. Packing efficiency is equal to number of particles per unit cell is 2. Volume of particle is 4 by 3 pi r cube divided by volume of unit cell is 64 r cube divided by 3 root 3 multiplied by 100. We can simplify that part. That part I will write here because space is not sufficient there. So you just see carefully how changes are making here. I will just look this here. So I write packing efficiency is equal to 2 divided by 1 4 by 3 pi r cube into 3 root 3 divided by 64 r cube multiplied by 100. This 3 into root 3 I have taken in numerator. This 3 and this 3 cancel. R cube and R cube also get cancelled. 4 into 2 is 8. 8 8s are 64. So it is nothing but root 3 pi. Root 3 pi divided by 8 multiplied by 100. Root 3 is 1.732. Pi is 4.312 into 100 by 8. And this you have to remember result 68% is the packing efficiency. Vacant space is 32%. In FCC, packing efficiency was 74% and vacant space is 26%. But here it is 60% occupied and 32% vacant. So packing efficiency wise, which is more efficient? Simple is less efficient than this BCC, less efficient than FCC, because this is 52.4%, BCC is 68%, and this is 74%. So which is most efficient? Cubic unit cell. It is face centered cubic unit cell because empty space is less here and empty space is more here. Less the empty space, more is the efficiency. More the empty space, less is the efficiency. This is space occupied and 100 minus 52.4 is vacant space. So all these three derivations, they are very important derivations. They can be asked in the examination. In fact, every year they have been asked. These derivations have been asked every year for 3 marks, sometimes 4 marks. Diagram, description, formula, and final answer are the important part here. Now we'll make one table, and in that table we'll write the important results of all these crystal systems. You can pause this video, complete this, or in printed notes also you can prepare it. In printed notes or examination, we should take 3 things as equal meaning. Particle, it's same as sphere, it's same as atoms. Because particles, we are assuming them as hard spheres, and particles, they can be atoms, ions, or molecules. So in this table which we are writing now is, we can write this simple cubic unit cell, body centered cubic unit cell, face centered cubic unit cell. The first point is the packing efficiency. Packing efficiency of simple cubic unit cell is 52.4. That of BCC is 68%. That of FCC is 74%. The second part, we can talk about the edge length, A value. A equals to 2 times of radius here. In BCC, we have to write 4 times of radius is equal to body diagonal, which is root 3a. That's why a is equal to 4 times of radius divided by square root of 3. For face centered cubic unit cell, face diagonal of 4 times of radius is equal to square root of 2a. That's why a is equal to 4 times of radius divided by square root of 2. And this 4 we have written as 2 multiplied by square root of 2 into square root of 2 by radius divided by square root of 2. We can cancel this, and we can write a is equal to 2 times of square root of 2 times of square root of 2 into radius, that equals to h length. Then third parameter we can write is about the radius. We can write that from this equation, radius is equal to h length by 2. Radius is equal to square root of 3a by 4, and radius is equal to a divided by 2 multiplied by square root of 2. Then fourth is the distance between nearest neighbor, that is denoted by d, and always that d equals to 2 times of radius, 2 times of a by 2, so that D is equal to A here in simple cubic unit cell. In body centered cubic unit cell, D is equal to 2 times of radius. 2 times of square root of 3A by 4. This is 2. So square root of 3A by 2. And lastly, D is equal to 2 times of radius. 2 times of radius is equal to A divided by 2 root 2, this 2 cancel. And we can write A divided by square root. So these are the various relations. Coordination number wise 6, 8, 12. Particle arrangement wise A, B, FCC, ABC, ABC. That already we know. Example wise, polonium, body centered cubic unit is lithium. Example: lithium, sodium, potassium, rubidium, cesium, and barium. And phase center, copper, silver, gold, platinum, nickel. So all these differentiating point you should know. Then only these calculations you can do this calculation with some speed. Right. So this is about the various types of crystal systems and their packing efficiency. Now only one formula. We'll see further because we'll use that formula again and again. You should make this table and remember this table because many questions in NEET examination, KCT examination, theory examination, you can use this table and you can solve it. Right. So this table is very important. Distinction between simple cubic unit cell, body centered cubic unit cell, and face centered cubic unit cell. Now what we are going to learn now is the density of the unit cell. Because just like formula of unit cell is a formula of substance, density of unit cell is density of that particular crystal. So this density, how to calculate it? First we must know that density of unit cell is equal to mass of unit cell divided by volume of unit cell. Now what is the mass of unit cell? Mass of unit cell is nothing but number of particles, which may be, again I am specifying, atoms, ions or molecules. Number of particles per unit cell multiplied by mass of one particle divided by volume of unit cell. This can be denoted by letter Z. Volume of unit cell is A cube. This is A cube. Mass of one particle, if it is atom, atomic mass divided by Avogadro number. If it is molecule, molecular mass divided by Avogadro. So this is the formula of density. What formula we are getting? D is equal to number of particles per unit cell. This is nothing but, again, if it is simple cubic unit cell 1, BCC is 2, FCC is 4, already we know it. atomic mass or molecular mass. A cube is the volume of unit cell. A is the unit length, and this is Avogadro. The volume of this density, unit of this density generally used is gram per cubic centimeter. This has no unit, it is just number 1 to 4. Unit of atomic mass or molecular mass is gram per mole. Unit of this edge length is centimeter, and cube of that is centimeter cube, and Avogadro number unit is per mole. So this per mole get cancelled. Gram get cancelled. Cubic centimeter get cancelled. Means unit of density is gram per cubic centimeter. Unit of this is atomic mass or molecular mass is gram per mole. Unit of edge length is cubic centimeter, and unit of Avogadro number is per mole. We know the value of Avogadro number. This 6.023. But for MCQs, we can take it as 6 into 10 raised to 20 because calculations we need to do at a higher speed. So this is very important formula. We have to use it, and this Z equals to number of atoms per unit cell. We have to read the question carefully, then use this value. Atomic mass will be given, edge length will be given, Avogadro number will be given. We have to calculate the density of the unit cell. So this is one important calculation we need to do. Many times question has been asked on it, and we have to mention one thing, that this D equals to this Z value, which is nothing but number of atoms per unit cell. For ionic substance, it is formula units per unit cell, and for NaCl it is 4, zinc sulfide it is 4, and CaCl is 1. I will write here the Z for NaCl is equal to 4, cadmium sulfide is also 4, and cesium chloride is equal to 1. Why it is so, we'll see in MCQs, but for this is the information we have to remember that these values are valid for ionic substance. For others, they will give in the question which type of cell we are talking about, and we'll use that information. So this is all about the density formula. So prepare all these 3 derivations correctly. Prepare a table and remember this density formula. And in next class, we'll solve questions on density. Be ready with the simple calculator, because we need to do more and more calculations to understand all the variations, possible variations in these questions. Thank you for watching this video.